great day so far. I'm happy to be here. My name is Katie Bennett. As Kevin said, I'm an MA candidate at Wesleyan University, and I will be moderating this hour session for the Interstellar Objects, Terrestrial Planets, Biosignatures, and Habitability. Speakers, I'll let you know if you're like over the time, but other than that, I'll just let you go. Our first speaker is going to be Jonathan Gomez Barrientos. He is an undergrad at Cornell, and he is applying to PhD programs right now. So if you're looking for students, pay attention to his talk. So Jonathan, you can go ahead and share your screen, and I'll start whenever you are ready.
Thank you, Katie, for the introduction. Just one moment. Ready. Can you hear me okay? And can you see my slides? Okay. Thank you everyone for being here today. I'll be discussing my work on retrieving the modern Earth's vegetation red edge from reflection spectroscopy. So some of you might be wondering, well, what is the vegetation red edge? Well, it is a region of rapid change in the reflectance or the albedo of vegetation in the near infrared. And there's an important feature because it is a surface biosignature of the modern Earth, and it has a significant impact on reflection spectra, which I'll demonstrate shortly. In this figure here at the top in purple, you have a reflection spectrum of an Earth-like exoplanet without clouds orbiting a sun-like star. This model assumes a constant surface albedo from 0.3 to 2.5 microns, which is what you're seeing in the bottom panel. The model in green here, however, assumes a wavelength-dependent Earth-like surface albedo, and you can see how the various features in the Earth-like profile impact the spectrum above. Here in red, you have the vegetation red edge, and you can see clearly how it drastically increases the brightness of the planet at around 0.7 microns. Now, if you recall, back in November, the Astro 2020 Decada was released, and it stated that the highest priority for the next couple of decades should be to develop a large space-based telescope to search for biosignatures in the atmospheres of Earth-like exoplanets. But given the impact of wavelength-dependent surface albedos on reflection spectra, we were wondering if such a telescope could also detect the vegetation red edge on an exo-Earth. And to answer this question, we first simulated observed reflection spectra of a self-consistent Earth-like atmosphere and surface using Picasso, which is an open source radiative transfer code developed by Natasha Battaglia. Then we developed and implemented a Bayesian atmospheric retrieval code to the simulated data at various signal-to-noise ratios to investigate what information we could infer from the data. So here in black, you have the simulated data, again with a wavelength-dependent Earth-like surface at RF70 and SN equals 10. If you run a retrieval on this data and assume a uniform albedo model in your retrieval framework, like previous retrieval studies have done, what you'll find is that you'll obtain biased results. The retrieved model, which is shown in red here, is heavily biased in the optical and the near infrared because the data lie outside 2 sigma. And this model also can't reproduce the feature you're seeing here that is caused by the vegetation red edge. So what this implies is that we should account for the wavelength-dependent nature of the simulated data in the retrieval in order to obtain unbiased results. And if you do so, what you'll find is you obtain a much better model, and you're also able to constrain the location of the vegetation red edge, which is what you're seeing in this bottom panel here. So here you have the posteriors of the surface free parameters. The lambda parameters are points between 0.3 and 2.5 microns, where there are sharp changes in the surface albedo. The AS parameters are surface albedo values themselves, so they vary from 0 to 1. And the key takeaway here is that the lambda 1 parameter is showing us that the red edge can be constrained at a signal to noise ratio of 5. And if you double the SN to 10, there are substantial improvements because we can constrain the remaining surface free parameters, and more improvements as you increase it to 15 and then finally 20. So to recap, the key takeaways here are that large space-based telescopes in the 2040s could extract wavelength-dependent surface albedo profiles, in addition to constraining the atmospheric properties of Earth-like exoplanets. The location of the vegetation red edge can be constrained at a signal-to-noise ratio of 5. the reflected light retrievals of rocky exoplanets should account for the wavelength-dependent aspect of surface albedos in order to obtain unbiased results. And finally, the wavelength-dependent aspect of surface albedos offers us an exciting opportunity to infer the surface compositions of directly imaged terrestrial exoplanets. Thank you for listening. I would like to take this opportunity to thank the McNair Scholars Program for funding my work. I would also like to thank my collaborators at Cornell and the CHAMPS collaboration for allowing me to share my work with everyone here today. I'm happy to take any questions now.
Thanks so much, Jonathan. That was great. It looks like we have a couple of questions in the chat. Robbie asks, nice work, Jonathan. Did you do this with clouds added?
Yes, we did do this with clouds, but due to time constraints, I wasn't able to share my results here. I am writing a paper on this research right now, and in that paper, we show the results of the cloudy spectrum.
Great. Laura asks, Jonathan, for your Picasso generated model, can you tell us more about what season, continental layout, viewing geometry you're assuming? And I was curious about that too, if you have to assume no ocean or anything like that.
So I think some of the assumptions are just that the phase angle is 0 here, and the Earth-like surface albedo here that we used here is just like an average. It was calculated using spectral profiles from the USGS and ASTER spectral libraries.
Great. Mark asks, note that the VRE might not be located at the same wavelength the terrestrial VRE is located, since planets might orbit different types of stars with different spectral energy distributions.
Yes, that's a great point. I'm glad you brought that up. I'm not saying that the vegetation red edge is the same for all vegetation. And there's no reason why plants around M dwarfs could have a red edge at longer wavelengths. And there's actually lots of papers that have looked into that. So yes, thank you for bringing that up.
Any more questions for Jonathan? Okay. All right, thank you so much.
Yeah, thank you.
Let's see. All right. Our next speaker is going to be giving a dissertation talk. This is Noah Tuchow. He is a grad student at Penn State, and yes, he is also on the job hunt. So make sure you pay attention. Noah, you can go ahead and share your screen whenever you're ready.
Okay, let me just get this set up. Thanks for the introduction. Second. Okay, can you guys see and hear me and see my slides? Everything's good?
Yep.
Okay, so I'm presenting my thesis research on potential habitability as a stellar property, assessing the habitable histories of stellar systems. And I'm Noah Tuchow at Penn State University, and I'm working with my advisor, Jason Wright, on this research. So the motivating question for my research is what type of stars are the best targets in research for biosignatures? We have a qualitative understanding about which stars might be the best to look at. So for instance, we typically prefer to look at sun-like FGK stars. We also prefer to look at older stars. This is because it took billions of years for complex life to evolve on Earth, and longer than that for Earth to potentially develop detectable biosignatures. So it makes sense to look around older target stars. We also have the influence to not look around massive stars or giant stars, and also neutron stars and white dwarfs due to their potential obstacles to habitability, although some of these could potentially be targets for search for biosignatures, although we'll be searching for very, very different types of life. So we want a way to quantify and formalize this intuition. So to first order, if you ask your average astronomer where exactly would we expect to find planets with biosignatures, the kind of go-to answer is the habitable zone, which I imagine most of you are familiar with the concept of the habitable zone, but it's the range of distances from a star where an Earth-like planet could support liquid water on its surface. And astronomers can calculate the distances of the habitable zone given the luminosity and effective temperature of a given host star. However, the habitable zone only gives a snapshot in time. Plants that currently reside in the habitable zone could have stayed there for billions of years, or they could have just entered it. So stars evolve and change over the course of their lifetimes, and as they do, so do their habitable zones. Over here in this figure, we have distance on the x-axis and age of a star on the y-axis, and one can see the habitable zone boundaries of a given. So this is the evolution of a sun-like star with roughly solar age. One can see that as the star ages, the habitable zone moves outwards, and there are planets, and if there were planets at certain orbital separations that would have started outside the habitable zone, eventually entered it as the star evolved. So from understanding the evolution of stars, we can essentially come up with classes of planets in the habitable zone. There are what we call continuously habitable planets, which are planets that have stayed habitable since their formation. And then there are what we call belatedly habitable planets. These are planets that enter the habitable zone from outside as the star evolves. And of these planets, there are actually two subclasses. There are inner belatedly habitable zone planets, which are planets that originate from interior to the habitable zone and enter it as a star potentially decreases in luminosity. And then there's outer belatedly habitable zone planets, which are planets that originate outside the outer edge of the habitable zone and enter it as a star increases in luminosity. So sometimes these outer belatedly habitable zone planets have been referred to as cold stars in the literature. So the relative sizes of these regions of the habitable zone depend on the stellar age and the mass of the star, and also on other stellar properties such as metallicity. So over here, we can see the habitable zone evolution for stars of two different masses. Here's a 0.5 solar mass star and a one solar mass solar analog, and one can see age on the y-axis for both these plots and the habitable zone distances as these solid lines on both these plots. And one can see that and also over here, this vertical dashed line is when we assume the habitability of the star, which is a potential assumption which we'll get into a little bit, which we're investigating currently. And so as you can see, as the star evolves, one can see that the continuously habitable region changes over time, and older stars have smaller continuously habitable regions, while more and more of their planets enter the habitable zone from outside. So this lower mass star, almost all of the planets in the habitable zone at a given age would be planets that enter from outside, would be these belatedly habitable planets. Whereas for a sun-like star, there's a much larger region of the habitable zone that remains continuously habitable, but there is still, as the star gets more luminous, planets from outside of the habitable zone eventually enter it due to the star's evolution. So why is it important to consider these regions of the habitable zone, to consider these belatedly habitable planets? So the fact is that many, if not the majority of planets that we find in the habitable zone will belong to this class of belatedly habitable planets. And one should not assume that these belatedly habitable planets are actually habitable just because they fall within the current day habitable zone. So these belatedly habitable planets may have several obstacles to habitability. Planets starting beyond the inner edge of the habitable zone may enter the habitable zone after they've already been depleted in volatiles. And so this is particularly an issue for low mass stars, which has been potentially hundreds of millions of years contracting and dimming before they settle onto the main sequence. And planets starting beyond the outer edge of the habitable zone may be difficult to thaw due to their high ice albedos. And the solar flux required to thaw these planets may lead them directly to a runaway greenhouse state. And there's also an additional obstacle to habitability for these cold start or outer belatedly habitable zone planets, in that they have difficulty outgassing a sufficient atmosphere because they have a global ice coverage. So there's several open questions about these belatedly habitable planets. Can these belatedly habitable zone planets actually be considered habitable? And how does the ambiguity of the habitability of these planets affect the search strategies for future missions to image Earth-sized habitable zone planets? And will these future missions be able to empirically test the habitability of these belatedly habitable zone planets? So just knowing if a planet is belatedly habitable or continuously habitable doesn't actually tell us how long it's spent in the habitable zone. And to search for biosignatures, we would like to find planets that have been in the habitable zone for an extended period of time. This is based off of the argument that life on Earth took around 2 billion years to produce oxygen as a biosignature, and then it took around 4 billion years for oxygen levels to become high enough to actually be detectable. So we've come up with this quantity called the habitable duration, which in this figure over here, you can see on the x-axis is distance from a star, and on the y-axis is the duration which a given planet, if a planet existed at a given orbital distance, that would be the duration which is spent in the habitable zone. And one can see that you have this kind of a plateau up here where these planets have stayed in the habitable zone for the duration of its star's evolution, whereas some planets also enter it from outside. And these red regions are regions that are outside the habitable zone, some of which contain planets that used to be habitable but are no longer habitable. So also, this curve is for a solar analog at the current age, and as a star evolves, so too does this curve. So this is for a solar model evolving in time. One can see that this curve changes as a function of time, and so it gets narrower and also taller, because it gets narrower and taller, and a larger portion of the planets in the habitable zone are planets which have entered it from outside. And so looking at this curve, the area under this curve might actually prove to be a useful quantity for determining the long-term habitability of exoplanets around a given star. So we've come up with a general form for biosignature metrics. And so this is the form of this quantity B, which is the integral of two quantities, H and gamma. Gamma is the planetary distribution function in some major axis and radius, whereas H is the probability of biosignature emergence as a function of distance and time. So these functions, H and gamma, lack empirical constraints and depend primarily on models and hypotheses and assumptions about planetary habitability. And for gamma, one can use any realistic distribution of like, say, a power law distribution for planets in the habitable zone, or any realistic planetary distribution function. And H can incorporate how long planets maintain their habitability, that quantity tau, the quantity, the habitable duration that I was talking about, throughout the evolution of the host star's luminosity and temperature. So these metrics serve to quantify our assumptions. So we've developed a flexible framework to assess how likely stars are to host biosignatures on their planets. And this is potentially useful for prioritizing target stars for future missions and interpreting positive or negative results from said missions. And we will investigate how different sets of assumptions affect which stellar populations are preferred by these metrics. So we find that different formulations of these metrics favor vastly different populations of target stars. So in this figure over here, we have metrics that are calculated for a grid of stellar models and mass and age. And the rows here are assumptions about H, the probability of biosignature emergence, and columns are assumptions about gamma, the planetary distribution function. So one can observe that different assumptions lead to different stellar populations being preferred. Here, the red values have higher values for these metrics, whereas the blue values are lower values. And so pay attention to the right-hand panels, which have a more realistic assumption for gamma. And one can see that it replicates our intuition that older low-mass stars are better candidates for biosignature searches because they would have potentially more stable habitable zones, and their planets would likely be in the habitable zone for longer. And one should also note that considering the duration spent in the habitable zone has a major effect. So this bottom column over here does not depend on the duration spent in the habitable zone. One can see that these panels look very different than these upper panels, which depend on the duration spent in the habitable zone. So we would like to rank stars according to these metrics, but we want to know how precisely we can determine the value of these metrics for a given star. And we find that uncertainty for these metrics comes from two main sources. There's systematic uncertainty in fitting stellar models to observations, but there's also uncertainties in the stellar models themselves. There's several open areas of research on stellar model physics and certain stellar models disagree with each other. So over here, I'm going to briefly cover a sensitivity analysis that we've been working on that compares the values of the metrics for different stellar models and different stars. So we simulate 3 stars at similar evolutionary phases, and we know the exact true values of their properties since they're simulated and not actual stars. We know like their exact properties. And these columns on the x-axis stand for different stellar models. So we determine how well each of these 4 different stellar models can recover the true values, since we know the actual true values from a traditional model. So over here we have a given metric. This is a metric that depends on the time spent in the habitable zone, including those bladely habitable planets. And one can see how well we're able to recover the actual true values, which are these dotted lines over here. So the filled markers show the recovered values from isochrone fitting. And one can see that the relative ranking of these metrics is relatively the same for all these different stellar models, but the actual values of the metrics themselves between the stellar models can vary quite substantially. And furthermore, the low mass star, which is the 0.7 solar mass star in these red markers, has large variation between the models and large variation due to systematic uncertainties, and that the ages of low mass stars are pretty difficult to constrain. So we found that stellar ages dominate the error budget. So isochrone fitting alone can constrain potentially more massive or solar mass stars, and we find that adding a constraint in ages can greatly improve our fit for low mass stars. So these unfilled markers over here represent the results of adding a 10% constraint in age, which is very difficult to obtain. But if you obtain that, one can see that the models agree much better both between models, and they have smaller systematic uncertainties. So independent age constraints are recommended for low mass stars because one can see that there's much less ambiguity for low mass stars when you have independent age constraints. So the major findings of our research are that our framework allows models of biosignature emergence to be quantitatively connected to target list prioritization, and this serves as a way to quantify our intuitions about which stars might be able to host planets that have biosignatures. And we found that different assumptions about biosignature emergence and the distribution of rocky planets affect which populations of stars are preferred in searches for biosignatures. And stellar age is potentially one of the most important factors in predicting which stars have the highest chance of hosting planets with biosignatures. And obtaining model-independent age constraints is difficult, but they're especially important for low-mass stars. So the next steps of our research will be these bladely habitable planets are a rich area for future research, and they make up a large fraction of planets in the habitable zone, but their habitability remains ambiguous. So I plan to model these bladely habitable planets and figure out what features one would expect to observe in their spectra. I also want to determine the statistical power to which one can empirically determine their habitability. This could be via future space-based direct imaging missions that might actually be able to directly image these planets and determine whether or not they host habitable conditions. So we would like to rank direct imaging target stars in terms of these metrics, and this would require us to more accurately determine the masses and ages of target stars to be looked at by future direct imaging missions. So the bottom line is that the metrics which we're developing could be useful for target star prioritization in a future search for biosignatures. And with that, I'll open it up for questions. Does anyone have any questions?
Yeah, what questions do you have for Noah? Oh, here we have to go. Thaddeus, I'm sorry if I'm not saying your name right, says, very nice talk. I might have missed it, but do you consider the effect of the changing spectrum as well as luminosity of the host star over time? And if so, does it have a significant effect?
Oh yeah, that almost certainly does have a significant effect, but our analysis has primarily been a first order changing the star's luminosity type of effect rather than taking into the detailed actual planetary science concerns of the planets themselves. So our next step is to actually go into the planetary science direction and actually model the atmospheres of these planets. And to do that, we would actually need to have a much more a detailed understanding of the spectrum of the host star and how that spectrum would evolve in time, as well as beyond just the bulk stellar properties of like the luminosity and effective temperature evolving in time.
Very cool. On that note, and I know that you touched on this in the beginning, but how does your model, or if so, could it in the future incorporate things in addition to the bulk properties like stellar activity and metallicity and other things that can change the spectrum received by the planet?
So we have a very general class of metrics, which I was talking about. Let me go back to the slide. Yeah. So it has these quantities H and gamma. So anybody could potentially. So these properties H and gamma are generally just a way to quantify our essential assumptions about the stars. So if you want to make a model of H, let's say, takes into account stellar activity, you could totally do that. It's an open-ended framework that could definitely be used for like to incorporate like any type of assumption that like you're dealing with that deals with like biosignature emergence. So our model hasn't really considered that in the past, but this framework could be applied generally to any type of assumption, such as like such as like stellar activity being a detrimental effect to the chance of finding biosignatures.
Very cool. Aaron wants to know, you mentioned planets around low mass stars may have lost most of their volatiles by the time they enter the habitable zone. With that in mind, do you think it's worth spending lots of JWST time looking for biosignatures on the TRAPPIST-1 planets? I think
what's actually more interesting is to see like is to kind of see whether or not we have proof of them losing volatiles or not. And so this could inform like for future missions, such as like like the future like Louvois and Habex concepts, like whatever becomes of that, it would be interesting to see whether or not these ember planets are good targets for those future missions. So I think that it is worth spending a lot of JWST time to characterize these TRAPPIST planets and see whether or not these TRAPPIST planets can actually be habitable, because they fall into the class of planets that potentially like were outside the habitable zone for like early in their lifetime, but entered it as the star dimmed. So it's useful to see whether or not these planets could actually still host large inventories of volatiles. It wouldn't be totally desiccated by the time like the end of the habitable zone. So I would say that it's a good investment of telescope time to determine whether or not these planets are habitable, and to that extent, I guess searching for biosignatures is also something that you could do.
Very, very exciting. Mark asks, can habitable exomoons be accounted for that might orbit gas giant planets outside of the habitable zone?
I would say yes, because our framework is flexible enough that this gamma does not necessarily actually have to represent the planetary distribution function. It could just be the distribution function for habitable worlds. So I could see potentially introducing a variation of like a gamma function that could include the effects of potentially having habitable worlds around gas giant planets, although that would potentially be a little bit difficult to formulate, but I could see that being done.
Yes, I agree with Howard. Fascinating. Any more questions for Noah? All right. Thank you so much.
Okay, thank you. Let me stop sharing my screen.
All right. Our next presenter is Michaela Leung. She is a grad student at UC Riverside. And without further ado, I will go ahead and cede the floor to her.
Thanks, Katie. Hi, everyone. Thank you for coming to my talk today, and thank you so much to all of the CHAMPS folks for putting on the seminar this week. Today, I'll be talking to you about my work on methyl bromide, a novel biosignature candidate. So methyl bromide is one member of a family of novel methylated biosignature gases that we're working on that have numerous advantages. The first of which is that they have low false positive potential. So there are no abiotic pathways to creating these gases that we're aware of. So these present a really strong positive signal of life if they were to be detected. Secondly, methylation is an environmental detoxification process, which we believe may occur in fundamentally different biochemistry, such as the types of life we might find on an exoplanet. even if they're very different from what we see here on Earth. And finally, there are two well-established members of this family that are well accepted as biosignature candidates, and that's methyl chloride and dimethyl sulfide from Segura et al. And Domagal Goldman, respectively. And we're specifically proposing these methylated biosignature gases as what we're calling capstone biosignatures. So gases that wouldn't necessarily be the first ones detected, but are really strong, positive supplementary indicators of a true biosignature, especially when paired with something like oxygen or ozone. So to conduct feasibility analysis of our biosignatures, we use a series of models, including the Atmos 1D photochemical model, the spectral mapping and radiative transfer code, and the planetary spectrum generator model suite. And we're using all of these models to perform vertically integrated simulated observables that directly connect the surface conditions with the actual biology that's going on at the surface here on Earth, all the way up to what we might see from instruments like JWST or other concepts. So jumping into a little bit of the results. So here I'm showing outputs of the photochemical model for a number of different star types. So on the left side here, you see results for methyl chloride. On the right side, you see the results for methyl bromide. The green vertical line in each case represents the globally averaged Earth flux for each species. And for each stellar type, we simulated a number of surface fluxes that are represented by the circle and then thick and thin horizontal lines on the plots. And we explore kind of a variety of flux cases, but the largest flux cases that we have explored are comparable to the most productive environments here on the Earth. So again, we're staying super connected to what we know is possible here. So the general trend in these results is that you see these really high levels of buildup for the methylated gases around M dwarfs, which is what we expect to see as a result of the photochemistry that occurs in the atmosphere of planets orbiting M dwarf stars. And this does follow the results that were originally described by Segura et al. 2005 in the initial description of methyl chloride as a biosignature. And you'll notice that the methyl chloride has a higher surface flux here on the Earth. This little green line is at a higher mixing ratio, but we actually see that for the TRAPPIST-1 cases, we see a buildup to a similar level for both methyl bromide and methyl chloride, which indicates that actually the relative buildup for methyl bromide is actually greater than for methyl chloride, which really kind of makes the methyl bromide comparable to methyl chloride in terms of the amount that they can build up in the atmospheres. We use the mixing profiles from the photochemical model to generate what I'm showing here, which are high resolution synthetic transmission spectra for TRAPPIST-1E, because we believe that TRAPPIST-1 is one of the optimal cases for biosignature analysis in the next decade. So here you see a couple of different absorption features at 10 microns, and then around 14 and 15. There's also some other absorption features that are at shorter wavelengths, specifically at 3.3 and 6.9, but they're difficult to see by eye because methane also absorbs in those same regions. And so hopefully this figure will just give you a sense for the size of these features, which are comparable to other potential biosignature candidates. We also use the planetary spectrum generator to perform signal to noise calculations, again for JWST observations of TRAPPIST-1E. And we use these signal to noise calculations to determine the number of transits necessary to detect methyl bromide or methyl chloride at their most optimistic production levels, and to do those detections with 3 sigma confidence. And our results suggest that we could detect methyl chloride or methyl bromide in under 80 transits, which is essentially the nominal science lifetime of JWST. Because the Miri noise floor is the main issue for detecting these gases, we're optimistic that potentially the FAR IR probe proposed by the Decadal Survey report, ground-based instruments or kind of new concepts and techniques that are just coming up now will be able to detect these gases in the late 2020s or 2030s, or NASA can just give us all of the James Webb time, you know, one or the other. So in summary, we think that these methylated gases are likely out of reach of James Webb, but we're really optimistic that we'll be able to get them with the next generation of telescopes, which confirms their status as, again, what we're calling these capstone biosignatures. That would really indicate strongly the presence of actually life rather than having any sort of false positives, such as other candidates might have. This analysis is nearing completion, so please look out for a paper on this topic in spring or summer of this year. And then finally, real quick, my advisor is hiring a postdoc. So if you're interested in this kind of work and you are looking for a job later this year, you can follow this link to the job ad and definitely reach out to me with any questions. And with that, I will take any questions about my talk. Thank you all so much.
Thanks so much, Michaela. That's really cool. Ravi says, great talk, Michaela. Methyl bromide is also used as a fumigant. Did I say it? Fumigant to control pests, industrially produced. It is passed out because it destroys the ozone layer. Did you compare your biotic flux with current industrial produced fluxes? I'm reading that in 1976, 71,000 tons of methyl bromide is produced synthetically compared to 50,000 tons by biology.
Yeah, that's a great thing to look into. We haven't looked into that, but I will definitely look into those numbers myself, because that could also be an interesting discussion about these gases being technosignatures as well, in addition to biosignatures.
Ryan asks, Michaela, how did you decide on 3 sigma versus something like 5?
Yeah, so I've done the calculations for both 3 sigma and 5. The 3 sigma are a little bit more optimistic. For 5 sigma, you would need something closer to like 100 transits or upwards of that. So optimistically, we're saying you could maybe do a weaker detection with James Webb, but for 5 sigma, we would really want to go to next generation concepts.
Ryan asks, nice talk. Does the SNR estimate account for the different contributions of various methyl bromide features or degeneracies with other species?
Yes, so the signal to noise calculations are basically looking specifically at specific wavelength ranges. So if I go back a slide, you could see that I have done these calculations for 3.3, 6.9, and 10.4 microns. So we're looking at specific features. If you were to like combine all of the features, I would say like the number of transits would potentially be even less, but I haven't kind of done the analysis for that.
And I agree with James's comment. It's cool that we're already talking about next generation telescopes and James Webb separately. Yes.
Yeah.
Any more questions for Michaela? All right, thank you very much. Okay, our next speaker is Carlos Cruz-Arce. He is a postbac researcher with the Southeastern Universities Research Association, and he's currently at NASA Goddard. He is also on the job hunt, and he's ready for full-time work starting in July. Carlos, go ahead and take it away.
Awesome. Thank you so much for the introduction, Katie. Can everybody see my screen? Yes, no?
Yep. Yes.
Okay, cool. So my name is Carlos Cruz-Arce, and I am a post-bac science researcher at NASA Goddard Space Flight Center. And today I'm going to be presenting on simulating surface albedos for reflection spectra of rocky exoplanets. So what does that mean, right? I'll tell you. So what you're seeing here is Enceladus. It is one of the most beautiful objects in the solar system, second to me and to my mother, of course. So this is Enceladus. We know Enceladus is mostly made up of water ice, right? And so a big goal of the astronomical community is to characterize exoplanets, specifically their surfaces. That's what we're trying to do. So we asked ourselves, are surfaces on faraway planets detectable? And if so, is there some sort of atmospheric parameter space where we can find these surfaces? And is there some sort of distinguishable feature that we can find in the spectrum of some planet, similar to like a gas spectral signature? And so keep in mind, we have Enceladus here. So we know Enceladus is mostly made up of water ice. And so what we did was we went ahead and we looked at the geometric albedo spectrum of 3 icy moons, Enceladus, Ganymede, and Europa. And we did this because we know that it's mostly made up of water ice, and we wanted to know, is there some sort of similarity between the geometric albedo spectra of these 3 moons and the actual spectra of water ice? And so here in this plot, what you are seeing is these 3 moons in blue, and then in orange and red is the actual reflection spectrum of water ice from the USGS library and the EcoStress library. And so off the bat, we can see that there's some similarities in the morphology of the spectra, which we thought was very interesting. Now, what if we add an atmosphere? Can we still see these features? So what we did was we created something like 17,000 models of geometric albedo spectra to explore a 4D parameter space defined down here. And so in these models are all essentially, we took the Earth and we stripped it of everything that makes it earthly. And we said, okay, now instead of having this beautiful diverse atmosphere, you're going to have an N2 atmosphere with one of these 4 dominant absorbers, only one at a time. And instead of your beautiful surfaces with cities and mountains and blah, 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 you're just going to have a very simple surface, either basalt or sand or silicates, seawater, frost, or grass. Grass being anything that's like vegetation with chlorophyll. And this is the mixing ratio and the atmospheric parameter space that we wanted to explore. And this is all in log space. And so we made our models. This is an example of a few of the models that we made. And so here, what you are seeing in both movies is in the lime green is the actual grass reflectance spectrum that we saw earlier in Jonathan's talk. And then in the dark green is our models, and in the blue is those same models, except with now with just a flat surface. And so when I say flat surface, I mean a flat albedo of 0.3 specifically. And so we can notice that as our pressure increases and as our mixing ratio increases, the morphology of the spectra starts to change. We can see grass very clearly, and then as our atmosphere gets thicker, it becomes harder and harder to see. And so the next thing we did was we ran retrievals on these models. We ran retrievals on these models to see where exactly those limits of detectability are within these models. And so in this table, what you are seeing here up here, this is our dominant mixing absorber mixing ratio. And then we have a different combination of some gas to some surface. And remember, these are all simplified models. And we made retrievals in these 4 band passes, the infrared, near infrared, visible, and near ultraviolet. And so we ran these retrievals, right? And the numbers inside the boxes, this is the pressure corresponding to the model. So for example, we're going to highlight H2O in grass because that's the most Earth-like. This is saying at a mixing ratio of H2O to N2 of -3 and a pressure of 1, that's 10 bars, we are saying we can detect grass in the near infrared and in the visible at this pressure and this mixing ratio. And now looking at this, you might be thinking, no, I don't believe it. That's impossible. You're saying you can detect grass at pressures of 1,000 bars for an SO2 atmosphere or CO2. And you'd be right. But again, these are very, very, very simplified models. So yeah, and we wanted to use this table to kind of narrow down what that spectral signature, if you will, would look like. And so here, going back to that grass column, we are seeing the right here, this plot on your top right, this is the limit of detectability according to our table from the slide before. And this is just one pressure below, and then this is one pressure above it. So this is the pressure of the Earth, 10 bars, 100 bars. And you can see at around, say, between 1.5 to 1.8 microns, and also at about 1.2 to 1.3 microns, there is something going on there that could tell us like, hey, we're pretty sure that there's grass in there, but we're not sure. And as a surprise, the blue line is actually Earth's geometric albedo spectrum. And so the claim, you could make the claim that maybe, just maybe, we are actually finding a grass feature within the Earth's spectrum, maybe. There is still ongoing work to determine just how realistic all of these models are. We need to make some more constraints to make these retrievals a lot more realistic. The next thing we'll do after that is calculate observing time required for one of these new generation space telescopes to actually detect a surface on one of these exoplanets. And future flagship missions like HABEX and LUVOIR will hopefully be able to use this work to help humanity find, characterize exoplanets and hopefully find life someday. Thank you. Any questions?
Thanks, Carlos. That was really interesting. What questions for Carlos? Okay. Jane says, very nice work. Carlos, what spectral resolution are you working at with your models? I ask as I wanted to know if the reflectance spectra are genuinely smooth or if they have features that you could see at high resolution.
So this is using a resolution of 500. So it's again, very simplified models. So what you're seeing, the smoothness of the spectra you're seeing is not realistic at the moment. But like I said before, there's ongoing work to make all these models a lot more realistic.
Any more questions for Carlos? Okay. Thank you very much.
Cool. Thank you so much.
All right, our last presentation before we go on to our break is going to be another dissertation talk. This is from Darryl Seligman. He is a postdoc at UChicago, and he is also on the job hunt. So Darryl, take it away.
Thanks, Katie. Let me share my screen. So can you see this okay?
Yes.
And you see my cursor, right?
Yes.
Okay. Well, thank you everyone for coming to this conference. You know, it's sad that we can't all be together in Salt Lake City at AAS, but I really appreciate the organizing committee for setting this up last minute. And especially to Aaron, thank you very much for setting this up for us, because I think everyone here really appreciates all of this. And before we get started, I also just want to say, everyone who's currently on the call, please stick around for the next session, because we're going to have, I know it's late in the day and we've got a lot of talks, but we have several awesome talks coming up in the next session, and I'll be chairing that session. So please stick around. And so what I'm going to be talking about, this is my dissertation talk. The dissertation was called From the Stars, an assessment of the scientific opportunities provided by interstellar objects. And so my dissertation was now a little while ago, but I guess the dissertation talk kept getting pushed back with the AAS and the COVID. But so this was work that I did at wrapped up at the beginning of COVID, and when I defended my thesis in 2020. And you know, I was kind of lucky, so I finished up grad school at Yale, and when I started graduate school, we knew about all of these minor bodies in the solar system. So we had things like the near Earth objects, which are shown here, you know, potentially hazardous objects. Things like Jupiter family comets, which when they get close to the sun have very bright, explosive cometary tails. And then you can go all the way out to the trans-Neptunian solar system, where there's a whole reservoir of Kuiper Belt objects. But during graduate school, when I was a third-year graduate student, the first ever interstellar object was discovered, Oumuamua. And not only was there one, but then there was a second interstellar object, the comet Borisov, which was detected just a few years later. And this was a really exciting time to be a graduate student and be able to devote all my time to this new exciting field of research. And I think in the next couple of years, you know, interstellar objects are really going to allow us to compare planet formation across the galaxy. So the story kind of starts in 2017. I was a third-year graduate student at the time, and this is the Minor Planet Electronic Circular that announced the discovery of Oumuamua. And so what you can see here, can you still see my screen? Did I mess something up here? Well, what you can see here is that the object has an orbit of eccentricity of 1.2. So this meant that it was a hyperbolic trajectory. And what I'm showing you here, this is just a schematic of Oumuamua's trajectory. And you're seeing kind of like the whole solar system here. And then if you zoom in on the inner solar system, shown in red is Oumuamua's trajectory. This is where it was when it was discovered, when it was kind of closest to Earth. And the hyperbolic nature of the trajectory definitively proved that Oumuamua was not from the solar system. So this was a piece of something that formed outside of the solar system and was just passing through our solar system. And it was immediately a global media phenomenon. Because kind of, these are just a few highlighted news articles from the couple of weeks right after Oumuamua was discovered. And the reason this was so exciting was that for the first time ever, we had the opportunity to look up close and characterize something that formed elsewhere. And it truly was, it was a crazy few weeks when Oumuamua was observable, and astronomers all across the world were scrambling to observe Oumuamua itself. So this is just showing you all of the positions on Earth where people were able to point their telescopes from the ground and get observations of Oumuamua. And another reason it was so exciting, not only was it kind of the first of its class, in every way that we expected an interstellar comet to behave, it acted exactly the opposite. So for one, Oumuamua had no evidence for a cometary tail whatsoever. So if you look at, this is just a deep image taken of Oumuamua, you can see it's clearly just a point source here, and there's no extended coma. And also, if you look at the composite light curve, so these are the brightness variations of Oumuamua over the couple of weeks when it was observed, you can see that it exhibited very drastic brightness variations. So the brightness was changing from brightest to minima by about a factor of 12, even though this was happening periodically every 4 hours. And this could be explained if Oumuamua had a very elongated shape. So what you were seeing was just, if Oumuamua was elongated and tumbling, you were seeing head-on versus edge-on projections of reflected surface light. But to get a factor of 12 in brightness variations, you would need something like a factor of 6 to 1 in elongation, which is much more dramatic than anything that we've ever seen in the solar system that formed naturally. And to make matters even weirder, it had a very significant non-gravitational acceleration in its trajectory. So what this basically means is that the astrometric positions of Oumuamua itself could not be explained purely by the gravitational influence of the sun. There must have been an additional force that was pushing Oumuamua away from the sun to fit that trajectory. Now remember, this happens in solar system comets all the time. So this is just comparing the measured magnitude of the non-gravitational acceleration of Oumuamua in black here with non-gravitational accelerations measured on solar system comets. And what's happening in solar system comets is you have ice that is sublimating and pushing a comet away from the sun. But for Oumuamua, just the fact, if it was outgassing, the fact that there was no coma observed is somewhat strange. And so I realized that if we assume that the non-gravitational acceleration was powered by the sublimation of volatiles, then there's a remarkable constraint on Oumuamua's composition, purely from the energetics. And this is kind of the most important question about Oumuamua, because if we could figure out what it was made of, then potentially we could figure out where and how it formed. And so the way the argument works is we know exactly how much energy Oumuamua received in the form of solar radiation. And we know exactly how much energy went into pushing the object and providing the non-gravitational acceleration. So all you have to say is that the number of particles in the outflow that pushes the object away from the sun, the energy for that has to be capped by the amount of energy you receive in solar radiation. And that energy goes into two sources. So for one, you put energy into the latent heat of sublimation, which is just to break apart the ice and turn it into a gas in the first place. And then you put energy into kinetic energy, where you take each individual gas molecule and heat them up to the sound speed. And so what I'm showing in this table is for several different volatile species. The important thing is F here is telling you what fraction of the surface of Oumuamua would have had to be covered in that particular volatile material in order to account for the non-gravitational acceleration. And kind of what you can see immediately is that the typical volatiles that are found in solar system comets like H2O or CO2 are not feasible. And the best accelerant by far would be solid hydrogen. Now, solid hydrogen, if we say that Oumuamua was made of solid hydrogen, this is kind of a weird thing, because this temperature here, this is the temperature of sublimation. So hydrogen sublimates at around 6 Kelvin. So you would have to go to almost the cosmic microwave background ambient temperature to freeze out solid hydrogen. And if this is the case, if Oumuamua really was a hydrogen iceberg, that would imply that Oumuamua basically has nothing to do with the solar system comets that we know of and have been studying for hundreds of years, because a protostellar disk doesn't get cold and dense enough to freeze out hydrogen. The only places in the galaxy where you could feasibly get cold and dense enough to freeze out hydrogen and form large macroscopic scale hydrogen icebergs would be the prestellar cores of the giant molecular clouds themselves. And if this interpretation is true, it's kind of exciting, because that would mean that Oumuamua was made of the most pristine and primordial material imaginable in the galaxy, and that material which actually leads to the initial conditions of star and planet formation. Now, if we just assume that Oumuamua was made of solid hydrogen ice, kind of amazingly, it would explain all of those mysterious properties. So for one, it explains the non-gravitational acceleration energetically, and would also explain the lack of coma that was observed, because you would never detect hydrogen sublimating at very cold temperatures. And then if we say that, Oumuamua was tumbling roughly every 4 hours, and we say that Oumuamua received roughly isotropic sunlight across the surface, then think about what this sunlight is doing. What's happening is it's hitting the surface of Oumuamua and removing hydrogen roughly isotropically. And so this also kind of amazingly will naturally explain the elongated shape. So what I did was I simulated the shape evolution of Oumuamua. When you start here, this is the aspect ratio of Oumuamua over time. Here at 6:1 was when it was discovered, with that very dramatic brightness variations and shape. And if you backtrace Oumuamua through the solar system, packing hydrogen shells back onto the body, you can see that it entered the solar system around here. This is a scaled down but accurate 2-scale version of that shape evolution. This process would naturally take a moderately shaped object and produce a very elongated shape. And it might seem a little counterintuitive, but this process is essentially exactly what happens to a bar of soap. So when, Katie's laughing, but yes, when you use a bar of soap, what you're basically doing is you are isotropically removing soap particles. And that, if you start with something that has a moderate aspect ratio, you're always removing a larger fraction from the short axis than the long axis. So that last, dramatic fragment you're seeing is just a natural product of isotropic ablation. And so the point is that under the assumptions of this model, Oumuamua would have entered the solar system with a much more moderate shape. So if you backtrace it to when it was entering the solar system, it was about doubled in scale, but it was an aspect ratio of about 2:1, which is almost exactly the same aspect ratio and size as near-Earth objects that we've detected, such as this object that a near-Earth object, York, which we've detected and characterized the shape of, which we know formed naturally. So I'm going to cheat a little bit because it's been a little while since my dissertation, but recently I also pointed out that carbon monoxide is also energetically a feasible accelerant for Oumuamua. And carbon monoxide is theoretically kind of a nice alternative explanation for Oumuamua's composition, because we see carbon monoxide in the solar system all the time. And we know that the solar system comets, many of them are very rich in carbon monoxide, especially those that form further out in the solar system. And so what I'm showing you here on the x-axis is the assumed bulk density of Oumuamua. And these are a reasonable range of cometary bulk densities. On the y-axis is the albedo, or the reflectivity of the surface, which scales with the size of the object. And the color here is telling you what fraction of the surface would have had to be covered in carbon monoxide ice in order to produce the non-gravitational acceleration. And the point is that everything below this line here is allowed. So energetically, this is also a very feasible accelerant. And then I also looked at the spin dynamics that would occur for an elongated object under the action of jets of carbon monoxide, or H2, but that covered the entire surface, that not only provided the non-gravitational acceleration, but would also provide rotational torques on the body. And we simulated this entire process. And it turns out that we could quantitatively reproduce the two salient features of the light curve. So this is Oumuamua's light curve over a few days when we had very good high cadence observations. And what you need to reproduce is the kind of factor of 12 in brightness variations, but also the constant 4-hour periodicity. And for a range of assumed geometries for the object, these are synthetic light curves that we made under the action of a rotational model, which included sublimation of volatile species across the surface. You can very well match the data. So these kind of interpretations of cometary outgassing are consistent with everything that was observed with Oumuamua. The weird thing about carbon monoxide, remember, is that there was a very significant non-detection of Oumuamua with the Spitzer Space Telescope. And this was about a month after it was discovered when it was leaving the solar system. And so that puts limits on the amount of carbon monoxide that could have been sublimating off the surface about 1 month after it was discovered. So the only way retrospectively to explain Oumuamua as a carbon monoxide-rich comet instead of a hydrogen-rich iceberg would be that Oumuamua was just sporadically outgassing, or it was undergoing variability in its activity. However, we did redo the astrometry to reproduce that non-gravitational acceleration, and it's certainly consistent with sporadic outgassing, although this theory of carbon monoxide is somewhat retrospective, to be fair. So the verdict is certainly not out about Oumuamua, and we're kind of stuck because the object is gone. But if you think about some of the potential hypotheses that have been posited to explain Oumuamua's provenance, the hydrogen iceberg interpretation would explain all of those mysterious properties. So the acceleration and shape, remember, naturally get explained in this interpretation. And there is reason for optimism here, because over the last couple of years, we have detected 2 interstellar objects. And there are the things like, it's clear that there is a galactic-wide population, and just the chance serendipitous discovery of these 2 objects implies that there are about 10 to the 26 similar objects in the galaxy. And it seems plausible or even feasible that there are 2 distinct populations of these objects. The one would be interstellar comets like Borisov, which are potentially form in protostellar disks and are ejected and could tell us about how planet formation varies around other stars. But intriguingly, if the hydrogen iceberg interpretation for Oumuamua is correct, this other population of dark interstellar objects could tell us about the most pristine and primordial material imaginable in the galaxy. And we should all be very excited because LSST should be coming online very imminently. And what LSST is going to do is give us an unprecedented increase in sensitivity to detecting these objects. So we're going to get several orders of magnitude increase in sensitivity while surveying the entire southern hemisphere almost every night. And so this should greatly increase the number of interstellar objects that we will be detecting on a yearly basis. And what I showed immediately after Oumuamua was discovered was that if we had had LSST online back in 2017 and discovered Oumuamua, which would have discovered Oumuamua several months prior to the discovery, we would have easily been able to send a rendezvous interception mission to the object. And what I'm showing you here on the x-axis is the hypothetical launch date of such a rendezvous mission. And on the y-axis is the delta V required to get to Oumuamua. So you can see that, remember, Oumuamua was discovered in October. And if we had sent something just at the end of July, a few months previously, we would have been able to get there with a delta V of just 4 kilometers per second, which is very doable energetically when you think about the types of delta Vs that have been used for missions to objects within the solar system. And this is showing you just what that hypothetical optimal energy mission to Oumuamua would have looked like. So in July, when Oumuamua was around here, this is Oumuamua in red, and the Earth was here in blue, LSST would have detected Oumuamua prior to this point, and we could have easily gotten there with just this impact or mission that would have required a delta V of about 4 kilometers per second. And such a mission would have, an in situ observations would have cleared up all of these questions that we still have about what Oumuamua was and what it was made of. How am I doing on time? Well, anyway, I think, yeah, I have like 5 minutes left. So we should be excited because not only is LSST coming online and we're going to be detecting more of these objects, the European Space Agency has recently selected Comet Interceptor, which will fly in 2029, which, if given the opportunity, would intercept an interstellar object. And NASA has put together a concept study called Bridge, which would be solely dedicated to the interception of an interstellar object. And so I'm going to end here, but I want to leave you with that you should definitely stick around for the next session, which is going to be starting with Devin Hoover, who is an undergraduate at the University of Chicago. And he has a paper with me and Matt Payne that's under review right now that you could check out on arXiv that he'll be talking about. But what Devin did was to simulate the entire population of interstellar objects that should be coming from the galaxy. And as they enter the solar system, evaluating exactly what type of, which of these populations will be detectable by LSST, with predictions for how many objects we should be detecting, and also how many objects would be feasible targets for an interception mission. So I'm going to end there and thank you all and take any questions.
Thanks so much, Darryl. That's fascinating. Mark asks, I assume there are no issues with the required abundances of these ices to form an object like Oumuamua.
Mark, which ices are you talking about specifically? Are you talking about hydrogen or carbon monoxide? He might not be able to unmute himself.
I'm talking about like nitrogen and all that. I think there's issues that in a giant molecular cloud, would there be enough abundance of any of these ices to actually form an object of that size?
Yeah, so I didn't have time to go through this, but I have backup slides somewhere. So Garrett Levine is a graduate student at Yale who I've worked with quite a lot in the last couple of years. And he went through kind of the detailed production mechanism for specifically for hydrogen icebergs in the prestellar cores of giant molecular clouds. And a nice thing about hydrogen is that there is no issue with the number density. I mean, there is, if the prestellar cores of the starless core prestellar cores of giant molecular clouds can produce solid hydrogen icebergs, then creating about 10 to the 26 of them in the galaxy is no issue. The main barrier for the hydrogen theory is simply getting to the frigid temperatures of the CMB temperature to freeze out hydrogen. And then with CO, additionally, that would be no issue because you need about 1 to 10 Earth masses per star ejected. And that's totally fine from what we believe to be kind of the composition of protostellar disks. And I haven't really gotten into nitrogen, but Garrett also has a paper about the nitrogen hypothesis, but nitrogen would be the one ice where the formation mechanism and cosmic abundances make it very difficult to fill a galactic reservoir with nitrogen icebergs. And he did have a poster or a talk about this at AAS, which was canceled, but there are several papers about this that he has. But that would have made, if Oumuamua was made of nitrogen ice, that would have made it a very unlikely detection. And we should expect that no more objects like Oumuamua should be detected during LSST's lifetime.
And then I guess why I'm here, I just have 2 further comments under that. Is there any issues of an object traveling for hundreds of millions of years surviving as a result of evaporation of the ices and also by impact erosion from cosmic rays over long periods of time?
Yeah, so Oumuamua basically had, I didn't talk about this at all, but actually the weirdest thing about Oumuamua is that the incoming trajectory was extremely slow with respect to the galactic local standard of rest. So that implies a very young, about 40 million year age. And in that original paper, I actually backtraced the trajectory. When I did the shape evolution, I backtraced the trajectory not only through the solar system, but also through the galaxy, taking into account the cosmic ray and ultraviolet radiation fields
Right.
that would
Yeah.
be exposed to. And Garrett looked at that a lot more in detail in his paper. And it's, I mean, interestingly, it's quite clear that Oumuamua was associated with the local like Carina or Columba associations. So that's completely, a 40 million year travel time is completely fine for an object that would have formed in these kind of star formations.
Relatively young. Nearby.
I think we probably have time for just one more question. Aaron asks, if built, would these missions sit around waiting for the next interstellar object detection and follow up if LST detects a lot of them? How do you decide which ones to send your mission to?
Yeah, I mean, my original proposal in this paper that we published right after Oumuamua's discovery was to, I mean, it's a little unrealistic to have something sitting on Earth ready to go and then launch and then get to an interstellar object with a few month lead time. And I think Devin is probably going to show, Devin has some results about this as well, but basically from Devin's work, we're seeing feasible wait times on the order of a couple of months between detection and when they get closest to the Earth, when you ideally want to have the interception happen. So my proposal was to have something sitting at one of the Lagrange points, ready to go, such that when you have a target, that gets detected, you could within a couple of months optimize the trajectory. And that is the exact same proposal that the same mission design that Comet Interceptor will be doing. The only difference is Comet Interceptor, because it's flying along with Ariel, has a much more limited delta V capabilities, purely based on the energetic mass budget. So Comet Interceptor's primary target would be a long period comet, which again, it's basically the same thing. You wait for a target, and then go when you find one. But if there's an interstellar object that comes that Comet Interceptor could get, you would do the exact same thing as this type of thing to get there. But I hope that we're in the situation in several years where we're choosing between exciting interstellar objects that we can get to. But I think for now, we just need to get a better handle on what the population actually looks like.
Thank you so much, Darryl. This was very interesting. I know that Laura said she's going to transfer the rest of the questions to Slack. And remember, we can continue to have this conversation in the Slack channel. So thanks so much. We'll go ahead and take a 10-minute break and reconvene at 4:20. Thank you to all of our presenters.
And stick around for the next session.